to Mr. Tom Creasy.
Good afternoon, everyone. As chair of the TRB Highway Capacity and Quality of Service Committee, I'd like to welcome you to today's webinar on Intersection Control Evaluation Part 2. This is the second of 2 webinars dedicated to the implementation of the new Highway Capacity Manual 6th edition as it relates to intersection control evaluation. Until recently, it's been the consensus within the profession that evaluation of interchanges and alternative intersections was best performed using simulation. The HCM now offers a range of deterministic tools, the only ones based on actual research, that can be applied, and it offers guidance on how to do so. As Courtney said, in today's webinar, we will address new methods for evaluating interchanges and alternative intersections, which include a new service measure and level service framework. We'll further address roundabouts as part of interchanges in urban street systems. Finally, we'll discuss several applications and examples of how these methods can be applied in practice. Again, welcome, and I hope you enjoy the webinar.
All right, thank you very much, Tom, and thank you, Courtney. My name is Jeff Shaw. As Courtney mentioned, I'm with the FHWA Office of Safety, and it's been my pleasure now to participate in both of the parts of the HCM6 webinar series that deal with intersection control evaluation. The way that the agenda lined up for this particular session gave us a chance to for me to provide a little bit of context as to what has gotten us here today in terms of ICE and why we think it's important that people are aware of how things have gotten us here and where things might be headed. So to start out, go back just a few years here. As many of you are probably aware, FHWA has been involved in evaluating and researching and promoting different types of alternative and innovative intersections for quite a long time. But just a few years ago, through our Everyday Counts Innovation Initiative, we focused specifically on advancing innovative intersections and working with AASHTO and state DOTs and local agencies across the country to encourage them to adopt in greater numbers different innovative intersection types, to build them and learn from them and really just become more familiar with them so that their confidence in considering them more often would be improved. We saw the advantages of exploring this to be multifold. First and foremost, all of these innovative intersections generally improve how people move across intersections. So we see this as an opportunity to not only improve safety and operations, but also as opportunities to create new space for people to walk and bike as well. So we're not looking at alternative and innovative intersections as just a fix for motor vehicles. We definitely see them as an opportunity to do better for non-motorized people as well. Of course, what makes a lot of the innovative designs similar is that they strive to eliminate or relocate or modify the conflict points, and that's really kind of the secret recipe for the really good safety benefits that most of these intersection types can deliver. And then last but not least, it's a way to look strategically at the type of control that you will choose for a particular intersection. And it's about synchronizing movements and what we like to call intersection choreography. So it's really a chance to reimagine how we design and operate intersections. Through the EDC2 initiative, we focused on a specific group of innovative designs that had a basis for being proven in the United States. We focused on the diverging diamond interchange, roundabouts, restricted crossing U-turns, median U-turns, and displaced left turns. Now, what all of these had in common, based on the experience to date, is that they all reduced severe crashes while also enhancing the efficiency of the operation of the intersections. Now, this first part, reducing severe crashes, this is enormously important. In 2015, we had over 9,500 people killed in intersection or intersection-related crashes just in the United States. And there are many, many tens of thousands more who are injured. And so having safer options for our intersection design and control choices is really truly a matter of life and death. Now, even though, as I mentioned, through EDC2, we focused mainly on getting states and local agencies to really build them and learn from them. And that proved to be an enormous success. We saw many, many states, over two-thirds of the states actually, advance the body of knowledge on 2 or more of those different innovative designs. You know, some states focused on roundabouts and DDIs, some states focused on all of those intersection types. But we learned a lot, and we learned a lot together, and that was really important. But even at that time, we knew that to sustain that success and to really truly institutionalize how we consider and implement innovative designs was going to require something more. And that something more has become known as intersection control evaluation policies and procedures. And really this is the stage at which a state says, we want to make sure that we're considering these innovative designs each and every time we go out and consider making a meaningful change to an intersection. So it's not just about waiting for that one problem intersection to come up and say, boy, we've tried everything, what else can we try? It's about saying, I've got an intersection, I need to go out and do something, whether it's because of economic development or a safety problem or a congestion problem. I want to consider all my options, okay? Not just what has become familiar. What is ICE? ICE is generally a 2-stage screening process. Really, stage 1 is what you would consider to be the new part of considering these designs. So stage 1 is a high-level assessment to consider all the different geometric and control alternatives. But through a quick screening process, using techniques like the ones that we'll hear about from Bastian, the idea would be to whittle a long list down to just a short few. Stage 2 then is the more rigorous assessment that would typically be done as part of preliminary engineering anyway. So, you know, there's not a whole lot of new here, but the whole idea of approaching it from this is the new concept. To give you an idea of what this looks like, and I realize that the text on the screen might be difficult to read, but just to give you an idea, so this is a 2-stage flowchart process that was developed by the state of Indiana. INDOT, during the EDC2 campaign, chose to develop what they call the intersection decision guide that walks through their ICE process. So they routinely consider all the different innovative intersection types and conventional intersection types, and they document that through this process. The criteria that's typically considered during an ICE, a lot of it should look quite familiar. What we're trying to do is bring a lot of these key performance metrics into the decision-making process as early as possible. So even in that stage 1 screening level, you know, we're looking for ways to bring safety operations, non-motorized provisions, and so on into that early consideration, into a scoping phase exercise. Now, what's really important about these performance criteria here is that the safety component is one that in a lot of places is new. And we're talking about explicit, substantive highway safety manual-based techniques. All right, we're not just talking about whether or not an intersection meets warrants for stop control or for a traffic signal. We're really talking about how is this going to change the safety performance of that intersection. Naturally, we're concerned about the operations, and we're going to hear about the new highway capacity models that can speak to that. But then all the other components of these performance metrics should all look familiar. And really, it's the first 4 bullets in particular: safety, operations, non-motorized, and freight. By another name, you could call this complete streets. Okay, so ICE definitely can complement that complete streets approach. But there are 3 additional very vital benefits to adopting ICE, and I just want to share those with you real quick. Number 1 is realizing your statewide safety goals. So each state, by virtue of participating in the Highway Safety Improvement Program, the Federal Aid Safety Program, is responsible for having a strategic highway safety plan. The vast majority, almost all the states, have intersections as an emphasis area. And so we know that intersections should be something that is on your safety radar. But the SHSP and the HSIP, very, very small piece of what a state or an agency can accomplish. But ICE, because it's not just a safety initiative, it's actually anytime we're touching an intersection, ICE would apply. It can be cross-cutting, and it can leverage all aspects of your highway program to deliver on safety. Now here's an example of one state's multi-year program. Okay, billions of dollars have been sliced and diced up into different program areas. Safety improvements over this 4-year period represent less than 1%. Now this is just for illustration purposes, but it's not atypical. So safety is a small component of a state's multi-year budget. We're not going to reach target zero if we rely exclusively on our safety projects as our means by which to make our system safer. We need to look for ways to put safety into all of the decisions we make, even the decisions that are about operations. Okay, so if we can leverage ICE by putting safety into ICE right next to operations, we've got a chance to really make some enormous gains across our programs. Number 2, the Safety Performance Management Final Rule. So as part of MAP 21 and the FAST Act, Federal Highways was told by Congress that we needed to develop a more performance-oriented federal aid program. One of the components of that performance-based program is the safety performance management. So as of this year, states now must set goals on their safety targets and then be evaluated against those goals in subsequent years. This applies to all public roads within a state. Okay, so if an ICE policy affects all of the intersections that a state is working on, and potentially even local agencies, then I hope you'll appreciate how this can be a way that we can actually work together and reach the goals that we have for reducing serious injuries and fatalities on our networks. And then finally, and certainly not least, is that we see ICE as a great complement to performance-based practical design efforts. So you've probably heard states talk about their desire to look at practical design as a way to perhaps save money, perhaps reduce the impacts, make their program dollars stretch a little bit further. That's great, okay? We want it to be based on performance as well, and to be performance-oriented so that we know how much more we might get by investing additional dollars in an intersection, or conversely, if there's a potentially better benefit cost by taking some of those dollars elsewhere, we would like to know that that's a possibility as well. So we see ICE being the intersections piece of performance-based practical design. And the whole idea of this is quite similar to what practical design has always been. The outcomes are building more good intersection projects rather than a few great ones. You've probably heard that line before when talking about practical design. But we want to make sure that that approach is grounded in those performance metrics that I talked about earlier, that we're focusing not only on the project but also on corridor and system benefits, and that we want to know what are we getting out of this investment today, in the near future, and long term, so that we can manage that accordingly. And by taking this approach, we see, again, innovative intersections are really part of the practical approach. So they no longer become alternative, they no longer become innovative, they become mainstream common solutions. So just to wrap up, the benefits of having an intersection control evaluation policy and approach in terms of what innovative intersection can provide. First, safety. We've got options that can reduce injuries and fatalities on our roads. We've got options that can improve operations. We know intersections are bottleneck points on our system, so anything we can do to address those operations is going to make it easier everywhere else. It provides opportunities to carve out more space, better space for pedestrians and bicyclists as well. And finally, it's a value-based proposition. So by looking at all these metrics and putting a price tag on them, you can see pretty quickly which alternatives are quite practical versus which ones appear to be over-engineered. And then finally, just to mention, as was mentioned in the introduction, more and more states are adopting ICE policies. We've got 5 states right now that have ICE policies in place. That's California, Indiana, Minnesota, Washington, and Wisconsin. We've got at least as many states developing ICE policies as we speak. So that would include Georgia, Florida, Pennsylvania, Nevada. And then we've got a number of states who are inquiring with greater frequency about ICE policies in their own states. So this is happening very quickly. It's a good thing. We want you guys to be aware of it, and quite honestly, we'd like you guys to help us out in states that maybe need a little bit of push. So with that, again, thank you for the chance to talk about ICE from a national level, and I will turn it over to Bastian.
Okay, thank you, Jeff. Okay, so with this great introduction and really setting the broader context of the ICE policy and the ICE framework, the remainder of the webinar focuses on the HCM6 methodologies and specifically these 4 aspects. First, I'll reiterate some of the ICE concepts and specifically how the operational analysis tools fit into what Jeff has been talking about to supplement the safety and life cycle costs and other performance measures. Then I'll give a brief overview of alternative intersections and interchanges and point you to some more resources for those who may not be as familiar with them. And then really dive into the HCM structure, what the interchange chapter looks like and used to look like in the HCM 2010, and then really focus the majority of the time here on the new capabilities and applications with these new procedures that are in the HCM 6. So this is to reiterate the national trends on ICE policy. So Jeff mentioned the 5 states with existing policies in place, and then the 3, at least 3 that I was aware of that are under development, really ties into the FHWA Everyday Counts initiative. Looking at the ICE evaluation process, really the key where the HCM and other tools can come in is on some of the evaluation and initial screening. So the idea is you start with a large set of alternatives. You want to take a very broad look at all your potential solutions, and then come up with results very, very quickly, much more quickly than is possible with a complex microsimulation analysis. There's a place for that, an application for that later on in the ICE process in later stages, but early on we're really looking at easier tools that we can use to compare these alternatives to whittle down our solution space. And really the idea is to have these decisions performance-based, and Jeff mentioned some of the performance criteria. Here's a little bit of a different list. And while the HCM clearly focuses first and foremost on the operational analysis, the HSM Highway Safety Manual with the key companion document to also help with the safety prediction. But in addition to operations, really the HCM also touches on the multimodal quality of service. For those of you who attended the webinar 5 in the series, a lot of multimodal pedestrian, bicycle, and transit methodologies for urban streets that are part of the HCM now, and that can also be incorporated into the ICE framework. And then also life cycle cost, a great product that came out of NCHRP project 3-110 that really takes intersection delay as well as safety and other costs into consideration. So really the HCM touches the ICE framework in various points. And so really looking at the 2-step process in ICE, the first is the assessment screening of a large solution space of alternatives. There's some very handy screening tools like FHWA's CapEx tools, and various states have adaptations of that tool available to really come up with some initial set of strategies. And then really I have HCM here at step 2, or maybe the HCM is somewhere in between step 1 and step 2, where we can really evaluate the operations of the alternatives. So we can predict traffic performance, we can get delay, we can get level of service, we can get travel times, we can get multimodal performance measures, and we have those performance measures in isolation as well as integrated into, for example, a life cycle cost assessment framework. That doesn't mean that there is no space in ICE. In fact, several state ICE policies have a third step that really then looks at a microsimulation approach. That's certainly feasible, but the idea is something is needed in between a planning level tool like CapEx and a very operational simulation-based analysis to really help contrast and compare some of these alternatives. So let's talk a little bit more about what these alternatives are. And really the great resource, one of the great resources that's out there are these alternative intersection and interchange guides that Federal Highway published in August of 2014. So they're available on the intersection website for Federal Highway. And so you can access these 4 guides there, as well as much information on tech briefs, and there's YouTube videos, a lot of information if you're unfamiliar with these guides. And really the thing I wanted to emphasize here is that these guides were not written in isolation. So they're really the culmination of many years of research, empirical research, that has been done on alternative intersections in the United States, including measurements on delay, on capacities, on saturation flow rate, on lane utilization factors. A lot of that information is contained in these guides and is also contained in the Highway Capacity Manual method. So not only is the HCM presumably a more quickly applied tool, it really is also the one that's anchored in empirical research and data, as Tom mentioned in his introduction, and really gives a lot of justification and added credibility to some of these methodologies. So the 4 intersection types that are really the alternative intersections, in addition to roundabouts that are part of everyday counts, that are reflected in the guides, and they're also all integrated in the new Highway Capacity Manual, are displaced left turn, which is also known as a continuous flow intersection, the median U-turn, which also comes by other names, the restricted crossing U-turn or ARCAT, and the diverging diamond interchange, or DDI. And so this slide shows various other names that have been used for these intersections, just in case in your state or your jurisdiction maybe a different expression is used. But really looking at a national map of, this is as of December last year, there's about 250 data points on this map currently, color-coded. This is an inventory that's maintained by ITRI, the Transportation Research Center at NC State. So I appreciate them making this available and sharing that with us here. You see about the highest number here, actually the median U-turns. There's about 100 of those, with a large cluster of them in Detroit, Michigan. But then there's about 65 DDIs on the order of 80 or so ARCATs, both signalized and unsignalized, and about 25 or a little bit more continuous flow intersections or displaced left turns. So while these numbers are not anywhere close to the several thousand roundabouts that we have across the country, they really are being built very, very quickly, and especially looking at the diverging diamond interchange, having over 60 or 70 DDIs open to traffic within just a few years of the first one being open in Springfield, Missouri is quite remarkable. So why this change? Where's the momentum coming from? And Jeff talked a lot about the safety benefits of these, similar operation benefits, really moving away from our conventional intersection that require lots of phases, multiple lanes to serve turning traffic, a lot of times having an 8-phase signal with 4 critical movements, a lot of lost time in between, resulting in inefficiencies, resulting in very wide and long crossing distances, travel paths for pedestrians and cyclists, and then the 32 conflict points that are shown in the bottom right here, including the very high-speed angle conflict potentials that are really linked to the very severe crashes. And really what all these alternative intersections, or these 4, have in common, that they all reduce, from an operational perspective, the number of critical phases, and a lot of them accomplish that by moving the left turns, whether that's through the directional crossover at the DDI for all movements, or of just the left turns at a DLT, or by rerouting some of the left turns to U-turn, as the case in the ARCAT or the median U-turn, some of the left turns and through movement. Really what all these have in common is they simplify operations, they simplify signal timing, they take away some of the high-speed conflicts, and really simplify operations. And so instead of having an 8-phase signal with 4 critical movement, it really replaces those with clusters of signals, most of them managed with 2, in some cases 3 critical phase signals. So we're replacing one complicated with a series of clustered, very simple signals. So then the question I would ask, if these alternative intersections simplify operations, why are we jumping to more complex analysis methods? Why, just because these things are new and unusual and we haven't seen them before, and maybe our preferred analysis software doesn't have an easy button that lets us analyze them, why are we jumping to complicated microsimulation analyses for the initial alternative evaluation? There are clear benefits of microsimulation when we're looking at visualization and communicating results to the public, the animation files that can be created. But in the stage of screening alternatives, why not jump to some simpler tools? And where I see the HCM really fitting in is somewhere between the initial planning level tools, where spreadsheets like the CapEx tool that is shown on the screen here provide a very quick initial assessment of the volume to capacity ratio of various intersections. Looking at I-Step 2, this is really where the HCM6 methods can fit in, and then potentially lead to a microsimulation analysis of the preferred alternatives, while potentially maintaining the HCM6 level of service framework that I will introduce in this webinar. So the idea is that the planning level method, as we're whittling down our solution space, provide initial estimates of expected performance, high-level design features, then move to an HCM analysis that balances that operational need with reasonable input needs, gives us quantitative information about delay and queue length and level of service, and then eventually move on to microsimulation, where we can do more customization and signal timing and have that visualization that, frankly, is required. The first time you introduce a DDI or a DLT in a new area, you probably want some of the visualization that you get out of microsimulation. So let's talk about the HCM structure and some of the basics in that methodology as it pertains to interchanges. All this material is contained in Chapter 23, Ramp Terminals and Alternative Intersections. In the HCM 2010, this was referred to as Chapter 22, Interchange Ramp Terminals. And you see it covers really a broad range of interchanges, diamonds, signalized, partial cloverleaf, single point urban interchange, even roundabout interchanges. And really what's new with the HCM6 edition is that it now also includes these 4 alternative intersections and interchanges that we've been talking about. The chapter also talks about some of the unique operational characteristics, which I'll introduce in this webinar. It has various design applications or analysis applications. And then it has now a level of service framework. It used to have one in the HCM 2010, but it's been revised now to really reflect the clustered nature of these intersections. That really we're looking at replacing one conventional intersection, one node, with potentially up to 5 nodes for a full DLT. And so a framework is needed on how to evaluate that. So here's the scope to take a look at what all the chapter, these figures are directly lifted from the HCM. And so here's the 4 new intersections. The reason that the grade separated interchanges and the at-grade alternative intersections have been included in the same chapter is that, frankly, they are operationally very similar in that there are multiple nodes or multiple intersections that act as a distributed intersection. Many software analysis tools actually use clustering methods and combinations to combine these signals. A lot of times, for example, the 2 crossovers at a DDI might be handled by the same, by one signal controller. And so even though there are multiple places where delays occurred, these are combined into one analysis chapter for a mini system or distributed intersection. And so then the chapter offers different parts, whether you're talking about grade separated interchanges or at grade alternative intersections, but using a common level of service framework. In terms of the organization, the old Chapter 22 that's shown on the left has now been divided into 3 parts. Part A in Chapter 23 in the HCM6 provides general level of service criteria and overview of the methodology. Part B then covers all interchanges in terms of the types, the signalized interchanges, talks about interchanges with roundabouts. The DDI is part of that chapter, that part. And then Part C is the new part on alternative intersections, where there's concept presented for the ARCUT, MUT, and DLT, as well as the methodology for vehicles, as well as discussion of extensions for pedestrian and bicycle analysis. So again, serving both the operational analysis as well as some of the multimodal characteristics of an ICE policy. There's also a supplemental chapter in the HCM 2010, as well as the HCM 6th edition, chapter 34. This is an electronic-only chapter that's available in Volume 4 at hcmvolume4.org. It contains a whole number of example problems that were available in the HCM 2010, talking about regular interchanges and diamonds and parclos and spuies, roundabout interchanges. All those example problems have been maintained, and now a lot of new material has been developed to talk about DDIs, examples for DDI with signals, with yield-controlled movements, and then various other alternative intersection types, all in terms of hands-on example problems where you can really understand and follow how the method is supposed to be applied. So I want to now talk, before going into the new concepts, talk about some of the older concepts that were part of this chapter, which in our surveys as we were assembling the HCM 6th edition, in user surveys and outreach, we learned that not a lot of practitioners have been using the old chapter 22. And so I wanted to spend just a few minutes introducing some of the key concepts that are really needed in this chapter. The first is an origin-destination framework, here shown in the example of various interchanges, the diamond and a couple of parclo configurations, where instead of a traditional turning movement count that we would have at a regular intersection, signalized intersection, we now have an origin-destination framework, where, for example, movement A is the left turn from the freeway onto the arterial street. Movement F is a right turn from the arterial street onto the freeway. And depending on the interchange or intersection configuration, that may either be a direct turn, or it may be a loop movement, or it may be a displaced left turn or a U-turn maneuver. So depending on the configuration, the movement stays the same, but the way it is integrated into the system of intersections may change. And so that impacts both the way inputs are needed, so origin-destination volumes across the interchange or cluster intersection system are needed as inputs, as well as all the outputs are reported by origin-destination pair, where it's broadly speaking a left turn or a through movement that goes through any and all intersections that are part of the distributed system. The second thing that chapter does, it considers impacts of demand starvation, and here's a typical or a common application of demand starvation at a traditional diamond, where what's shown here as the westbound through movement at the left ramp terminal shows a green signal indication, but because of the signal timing on the eastern ramp terminal, there's no traffic that can realistically reach that green signal indication. And so as a result, the calculated capacity, or the G over C, the green to cycle length ratio, effective green to cycle length ratio for that western outbound through movement is really overestimating the true capacity because a lot of it is not being utilized. So the method contains explicit estimation of that demand starvation effect, which is then subtracted from the true available capacity to get a realistic estimate of delays and queue lengths. Another key characteristic and key feature of this chapter is lane utilization. And this is where I would argue the HCM can really also be a key calibration aid for those of you that are doing microsimulation analyses. Because really in microsimulation, depending on how the model is set up, the lane utilization for top left, a heavy left turn at the diamond interchange, as opposed to bottom left, a heavy right turn at a partial cloverleaf, those two movements will create an imbalance at the external approaches to the interchange, which may or may not be reflected in the microsimulation. And so calculating these lane utilization factors that are based on field data in the HCM can be a key calibration tool. Bringing in some of the new configurations on the right, we actually have 5 different lane utilization models for diverging diamond interchanges as a function of the lane assignment and the proportion of left turns that really predict how much traffic will pre-position before ever reaching the DDI to make the eventual left turn onto the freeway. Another key consideration in this chapter for all of the intersection interchange types is saturation flow rate. For those of you familiar with the HCM and signalized intersection analysis, we commonly adjust saturation flow rate for effect of heavy vehicles or for the effect of a right turn or a left turn and many other factors, but presumably geometry impacts saturation flow rate. Well, because of that, we have left turns as well as U-turn maneuvers here at this ARCUT that have very different saturation flow rates in a conventional intersection. And so those saturation flow rate adjustments need to be taken into consideration. This is, again, a key tie into microsimulation where the U-turn crossover may or may not have the correct simulated capacity. The HCM saturation flow rate adjustment factor would be a great way to test that. Similarly, the DDI crossover. It is not a straight movement, a straight shot through the interchange. Drivers sometimes go through a reverse curvature, then switch lanes to the, switch directions, switch sides to the crossover. And so that results in a drop in speed and a drop in saturation flow rate that were identified at about 11 DDIs that we looked at across the country. And then finally, yield-controlled movements. We have obviously other intersection types like roundabouts that have yield-controlled entry points, but many of our alternative intersections, for example, top left and an ARCUT with yield-controlled left turns, or on the right, a DDI with yield-controlled right or left turns. There's several DDIs across the country that have yield-controlled movements from the freeway, or on the bottom left, the MUT at the U-turn. A lot of times those are actually stop signs, not yield signs, but still we have some unsignalized movements that need to be taken into consideration. And so the chapter provides methodologies for this, including gap acceptance parameters that, again, could also be a basis for then eventually calibrating a simulation model. Because presumably most agencies, most analysts that may look at their first ever simulation model for a diverging diamond may or may not have gap acceptance data for a left turn off the freeway from a DDI. The HCM actually provides those parameters based on field data. And so as a result of this, really chapter 23, at the heart of it, the method is no different from the signalized intersection procedure that many of you are likely familiar with. But because of some of these unique configurations, the various interchange and intersection forms have some other adjustments that are summarized here in this exhibit 23-4, where it just gives you kind of a map of how the chapter works and what are the types of adjustments that are applied to one or more of these intersection and interchange types, just to be reflective of the field observed configuration and conditions at these intersections. Okay, so that brings us to the last part in terms of new capabilities and applications. There's really three components of this. First, I want to talk about the level of service framework, which is probably the aspect of this chapter that impacts many of you most directly. Presumably you are reporting level of service, even though I should emphasize that the HCM provides a whole host of performance measures that are arguably more descriptive and more telling than just a single letter grade. But I, at the same time, of course, recognize that level of service is an important value to get out of an analysis. And so I want to introduce you to that framework, and then talk a little bit more about the new DDI method as well as the new alternative intersection methods. For the level of service framework, we now have a new service measure that was introduced as part of the HCM 6th edition that's called experienced travel time, or ETT. That experienced travel time is the sum of all control delays and any extra distance travel time that is experienced by rerouted movements. In other words, if you envision, for example, in the bottom left, this left turn at an ARCUT from a minor street to the major street at a traditional signalized intersection, that would have been a direct left turn that experiences delay only at what's labeled point 2. At an ARCUT, that movement presumably experienced delay at point 2, then a travel time between 2 and 3, then some delay at point 4 at the U-turn, and then some out-of-direction travel time between 5 and 6. Most of the time there's no additional delay as they go through this other signal, but there's another potential for delay here. So the ETT service measure would be the summation of all these individual pieces. In the bottom right, the example of a diverging diamond, again a left turn, in this case from the freeway onto the arterial. You would have some out of direction travel because you're moving at an angle as opposed to approaching the intersection straight at the Y line. You then incur some delay here at points 1 and 2. You have then some travel distance and then some additional potential delay at point 3. And so these would be added together to obtain this ETT measure. Looking at a conventional diamond, again, the relative comparison for this measure is a direct left turn from the center of the intersection, or kind of Y line to Y line. So a diamond interchange, especially a spread diamond, where the ramp terminals might be a significant distance away from the freeway, as is shown here by that green line, that out-of-direction travel distance would also be added into the ETT calculation. In this particular case, it probably is not a high number, maybe 2 or 3 seconds, but for the sake of fairness, it is included for any out-of-direction travel away from the Y line for these interchanges and intersections. So that service measure, ETT, then becomes the sum of the control delay and that EDTT, the extra distance travel time. And that value is then compared to various level of service thresholds that are also shown on the next slide. For signalized interchanges, there's no change from the HCM 2010. The thresholds are about 1.5 of what a signalized intersection has. That is because drivers presumably are going through multiple signals. At a typical diamond, there would be 2 signalized intersections. But since they operate as a cluster, the committee felt that the threshold should not be multiplied by 2, but instead by 1.5. All of the alternative intersections have the same value as signalized intersections, so level of service F happens at 80 seconds. And then interchanges with roundabouts is again consistent with the HCM 2010, but the thresholds are a little bit higher than an isolated roundabout, again because you have a cluster of multiple roundabouts that act as a system, so a little bit added delay is permitted there. And so this is what it translates to in terms of the level of service tables. The top is signalized intersections, the middle is alternative intersections, and the bottom are interchanges with roundabouts, and you see the thresholds there on the left. The other thing to note here in the level of service framework, just as many other chapters in the HCM, you get an automatic level of service F if volume of capacity of any lane group in the interchange or intersection exceeds 1. So any overcapacity movement, even if it's a low volume movement from a side street, results in an automatic level of service F. And then new in this chapter is the R sub Q, which is the Q storage ratio, which is an explicit test, for example, at a diamond interchange, whether the left turn Q between the 2 ramp terminals spills back into the upstream intersection. Whenever that Q storage ratio exceeds 1, that is also an automatic level of service F. Talking now about some of the new capabilities for the diverging diamond interchange. So a DDI with a crossover at each terminal. There's really 4 major pieces that I'll talk about. Saturation flow rates, lane utilization, additional loss time, and yield-controlled movements. I should note that all 4 of these are based on empirical research. So Federal Highway sponsored a research project that looked at 11 of the first DDIs that have been open to traffic in the country, collected a lot of field data, and then developed models specifically for DDIs in the United States, making, again, this a robust and empirically anchored method that has empirical basis as opposed to some of the simulation analyses. First, for the saturation flow rate adjustment, there's an F sub DDI factor of 0.913, so about 8.7% drop in throughput at the DDI because of the curvature and the crossover nature of the movement. Most of the time that capacity is well made up by the fact that the DDI only has 2 critical phases and therefore provides more green time. But each second of available green time has this reduced capacity because of the crossover movement. Looking at lane utilization, based on the downstream lane assignment at the internal crossover, as well as the left turn demand ratio, field data suggested potentially highly unbalanced pre-positioning the lane utilization at the upstream approach, so the first crossover, which is shown by the red boxes on the slide. And so the HCM contains 5 different models for 2, 3, and 4 lane DDI approaches with a mix of shared and exclusive left turn lanes that are estimated to get a lane utilization adjustment factor based on the left turn demand ratio, which then impacts the capacity and the calculation of delay at the first crossover. The next big piece is additional lost time. For any interchange, this is not just the DDI, but for any interchange, if you have internal queuing, which of course is a function of your signal timing and potentially poor progression. So anytime you have a downstream queue that's internal to the DDI, the available capacity of either the external through movement entering the DDI or a left turn from the freeway is adjusted by the time that the internal queue still exists. So if there's a queue and the upstream phase starts and the available queue storage space is taken up, then additional lost time is incurred by the upstream phase, effectively reducing the available capacity of that movement in the interchange. That could presumably be remedied with better signal timing and better coordination and longer green times, different splits and offsets between the 2 crossover signals, but the HCM method and software explicitly account for that. The next is additional lost time because of the ramp phasing. Many DDIs across the country are timed with overlap phasing that recognize that the green movement outbound in this example at the DDI really has 2 different clearance intervals. It has one relatively short clearance interval that's needed to clear the crossover itself, and at that point, after that clearance interval has elapsed, the inbound movement, the solid green arrow in this slide, can proceed. But really there's an additional clearance time that's needed for the external movement to also clear, in this case, the right turn off-ramp conflict. And a lot of times that is handled through overlap phasing. In the HCM, that additional time is handled as additional lost time. So where phase 7, the through movement here, would get full capacity, and then phase 8 in this nomenclature, the ramp green is adjusted with an additional lost time that accounts for the overlap with the additional clearance time. And this is explained in the chapter with several examples to illustrate that point further. And then finally, yield-controlled movement. I mentioned earlier in the presentation that we see quite a few DDIs across the country that have yield-controlled right turns as well as yield-controlled left turns. And whenever that is permissible from a safety perspective, when sufficient separation and line of sight is provided, these yield-controlled movement actually can result in higher capacity than a signalized intersection, signalized turn, especially if right turn on red is prohibited at those movements, because then the yield sign gives a combination of different regimes, which is what's reflected in this methodology. So the notion, the yield-controlled movement, the capacity is the sum of the individual capacity of 3 flow regimes. The first is a regime where the turning movement is blocked by a platoon that comes from the crossover, for example, so the capacity during that regime is typically 0. It's then followed by a gap acceptance regime where you have some vehicles entering the DDI, but the turning movements are able to accept gaps in traffic the same way that they would do at a roundabout, so that the capacity calculation for that regime is very, very similar to the one we use at roundabouts, just with different critical gap and follow-up time parameters. And then finally, a no opposing flow regime, which in our field estimation, our field evaluation showed almost free flow conditions. At the yield time, drivers recognize that there is, for example, an outbound movement in the crossover that blocks any potential for conflicting traffic, and so those right and left turns get very high capacities during those flow regimes. So the way this methodology works is it calculates the capacity for each regime in isolation, and then computes an overall capacity as the probability weighted average of those 3 regimes. This is the first time a methodology like this exists in the HCM. It has potential application even beyond the DDI to, for example, a signalized intersection with a channelized right turn lane that might be yield controlled at the downstream merge point. It hasn't explicitly been designed for that, but this is a significant step forward in the HCM to also evaluate yield controlled movement with mixed flow regimes. Okay. So moving on then to the alternative intersections, I'll talk a little bit about the computational steps for arc cuts and median U-turns, and then finish up with the displaced left turn. The HCM method for arc cuts can evaluate four-legged arc cuts with traffic signals, as shown here. So these are signals at both the left turns of the main line at the main intersection, as well as signalized U-turn movements for the side street, through movements and left turns. There's also a method for unsignalized arc cuts, where the main intersection left turns may be controlled by yield movements, and some of the U-turn maneuvers may actually be merge conditions. Typically, these rural arc cuts that are unsignalized are have a much larger intersection footprint, so that would really impact variables like the extra distance travel time, which would all be considered in this methodology. And then for median U-turns, again, the method evaluates either a signalized median U-turn, or it could be a median U-turn with stop signs at the U-turn locations. That's all part of the scope of the methodology. The framework is a 10-step methodology, not unlike that of the signalized intersection analysis in terms of coming up with volumes, except for that they're now OD volumes, as mentioned earlier, coming up with lane groups and lane utilization, adjusting for signal progression, and then really evaluating the performance for each individual junction. So the biggest thing that makes this method maybe more complicated or time-consuming is that even though each intersection is a lot easier, presumably a two-phase signal, the computations have to be done multiple times, and then everything gets added together with the estimated extra distance travel time, any weaving delay that occurs at an arc cut, the movement from a right turn to the U-turn opening, and then calculating the ETT, the experienced travel time, to get to the level of service. That means there's some new input data that is needed to do these analyses. So it starts with some of the same input data that we're used to for signalized intersections or two-way stop-controlled intersection, depending on the type of control. But we now need things like U-turn volumes, the median width, which impacts saturation flow rates and gap acceptance parameter, that travel distance, so the spacing, and then the free flow speed along the major street, which is used to calculate the extra distance travel time if the U-turn is placed about 600 to 800 feet from the main intersection. You need to specify how fast is traffic moving over those 800 feet to calculate a corresponding travel time. Some other inputs, the weaving delay. There is currently no method for evaluating the delay of a two-sided weaving maneuver. The slide here suggests potentially looking at the freeway weaving method, although the committee has gotten some criticism and pushback on that. So this is actually an area where some of the state agencies are doing some additional work and research. And there's also an upcoming NCHRP project that looks at arterial weaving capacities that could be plugged in here. There's U-turn saturation flow rate adjustment factors that are a function of the median width. So you see here with a very wide median, you end up with less of a saturation flow rate adjustment than for a narrow median. So the defaults are available in the method, but you have to specify your geometry. And then here's the gap acceptance parameters for your U-turns, which could also be a good input as you're calibrating the simulation model. So using that framework, another example of that EDTT, the extra distance travel time, in order to estimate how long that is, you have to calculate these two distances, D sub T, which is the distance from the main junction to the U-turn crossover, and then D sub F, which is the reverse direction. Typically, those two are the same. You need the free flow speed for the major street, and then some potential delay due to deceleration or acceleration in turns. That is whenever the right turn is controlled by a merge, the way it is shown here. So any acceleration delay could be added here. For a stop sign or signal, that acceleration delay is already included in the control delay, so it doesn't need to be added here. But for any free flow right turn bypass lane with a merge, there's the potential to add additional acceleration delay. And then finally, for the displaced left turn, there's a series of configuration. The method is really designed for the partial DLT. There's a typo there, not DTL. The partial displaced left turn, where one of the direction has the left turns moved. But the method can also be adopted to a full DLT, which essentially doubles the method, and it's evaluated as two half DLTs. So the method itself doesn't change. So for the half DLT, the method assumes three signalized intersections that are evaluated using the urban street segment method in the HCM, as well as the signalized intersection method. So the DLT is probably the one of the four that is the most similar to the existing methodologies, with really the biggest difference being is that it's applied 3 times as opposed to just once. And then it's a matter of record keeping and configuring software correctly to get these estimates, to get the sum of the delay for those 3 movements, 3 intersections. A lot of times at a DLT, signals are timed where the displaced left turns only stop once. That is where the initial term for this intersection, continuous flow intersection, or CFI, came from. That after an initial stop for the left turns at the crossover, then the offset is in a way that there's no secondary delay incurred. So really for these left turns, a lot of times it's just one delay point, even though it goes through 2 signalized intersections technically. There are some adjustments for saturation flow rate. The left turns at the supplemental intersections, there's a recommendation to actually use the right turn saturation flow rate adjustment, even though it's technically a left turn maneuver. The reason for that is that the geometry ends up looking a lot more like a right turn, so a tighter geometry as opposed to a left turn, and therefore research found that the right turn adjustment is really more appropriate. And then there's some guidance in this chapter and discussion on the signal offset and how that might be computed to make sure that really that secondary delay as the left turns after crossing over, as they go through the main intersection, there's no second delay incurred. So there's actually some signal optimization discussion now part of the HCM. For a full DLT, essentially it's analyzed as 2 half DLTs. So first the north-south street, then the east-west street, and then the results are aggregated. It ends up being 5 signalized intersections. For each of those, each movement has some delay, and then using the ETT framework, all those delays are aggregated to come up with a total delay. The DLT, as opposed to the other configuration, has very little extra distance travel time. There's a little bit of a displacement, but there's not much additional out-of-direction travel time, as is the case for the median U-turn or the ARCA. So summarizing here, there is a lot more information that I didn't have a chance to cover. For those of you who are new to this methodology, I especially encourage you to take a look at the example problems that are part of the electronic volume 4, so hcmvolume4.org, which is free to access to anyone. You can create an account, a free account, even if you don't own a copy of the HCM 6th edition. So you can take a look at these 17 example problems. Many of these were specifically developed for the new alternative intersection methods. They cover the diamonds and the park close and the spuies and the roundabout interchanges, but now also have the DDIs as well as the ARCAT MUT and the DLT. So lots of information there to really cover the whole spectrum of what this chapter could be used for. So in closing, before we turn it over to questions, bringing this back to ICE, there seems to be a real opportunity here to integrate these HCM procedures as part of a late step 1 or an early step 2 in an ICE analysis. mid-level type of analysis between your initial screening, where you might use a tool like CapEx, and the final alternatives in a simulation environment. These methods are anchored in empirical observations of alternative intersections in the U.S., which is really a very, very important characteristic. And so even if you use other tools, the HCM, as well as some of the underlying research that is available on hcmvolume4.org, can be really helpful resources for you to take a look at. What are the gap acceptance characteristics for U-turns or for yield-controlled movements at DDIs? What are the saturation flow adjustment factors, and et cetera. As more alternative intersections come online, and as your respective agencies have more, there is an opportunity to directly calibrate these methods, which is another key feature of really any of the HCM methods, where of course we have a saturation flow rate adjustment method that you can use in a planning context. But if you have field measurements of sat flow rates, if you have many DDIs in your jurisdiction and you know what the capacities are, you can of course plug those in directly as an input and therefore calibrate these HCM methods to local conditions. The level of service framework, I feel, is really a key contribution here. Even if you're using a simulation analysis, somehow you need to report the comparison, the results, and somehow you need to compare the operational results between an alternative and a conventional intersection, or between these different intersection configurations. And there's a framework on how to do that. Even if you don't like the letter grade, you can still use the ETT number that's calculated. And then the last thought is that really with all this, the software implementation will be key. And so I encourage all of you that are interested in these methods to also lobby your respective software developers that are implementing the Highway Capacity Manual to really make sure that they're integrating these methods. They are new, they are maybe not the status quo, but they are very powerful. And recognizing that most of you will use the HCM through software implementation, I really look forward to seeing some of these. Some of the developers already have these implemented, and it really would be nice to have nice interfaces and really usable tools that we can use to take full advantage of these new methodologies in the HCM. So with that, I'll put a quick plug-in for the last webinar in this series that will be offered on March 21st on corridor planning powered by the HCM6. So looking at a combination of the urban streets and freeway facilities methods. And then I'll hand it over to Courtney for questions. Thank you for your time.
Great. Thank you so much, Bastian and Jeff and Tom for your presentations, and for Tom for introducing the webinar. So now we will move on to our Q&A, and I will take back control of the screen. Hold on one moment. So we will begin our Q&A portion of today's webinar. So if you haven't already, please type your questions into the question pod located in the control panel. We will try to get to as many questions as possible before today's webinar ends. And if you're hosting a webinar today, reach out to the attendees at your location and have them send you or write down questions for the presenters that you can type in on their behalf. All right, so I'll go ahead. We already have several questions that have come in, so we'll go ahead and get started. How would you get OD information?
This is
I can take that.
Okay, go ahead, Sebastian.
No, go ahead, Tom.
Well, you're going to have to come up with your own OD information. There are a number of ways to get it. There are several options for third party, for actual field measurement using different technologies, different vendors. You could possibly use matrix estimation as part of a travel demand modeling package, but that will be an input that the analyst will need to to insert to the process. So you're going to you're going to need to come up with your own origin destination information, and it should be based on actual field data. Bastion, if you want to add anything to that, please do.
I would have answered it very similarly. Depending on your type of analysis, you may actually, if let's say an interchange study is part of a broader planning process, you may actually end up with volumes that come out of a travel demand model, and then you actually would have the origin destination volumes. And there's other ways to synthesize the OD method. There's actually in volume 4 in chapter 34, there's some guidance on how to do that. If you're unfamiliar with it, but it's not unlike what I think many times we would do an analysis for an interchange, even a traditional diamond interchange. We would first develop OD volumes, and so there's a few different ways to do that.
Great, thank you. Another question that has come in, if a roundabout interchange LOS threshold uses signalized intersection thresholds as a starting point, why does HCM 6th edition still use unsignalized intersection thresholds for a single roundabout intersection instead of using signalized thresholds for LOS?
Yeah, that is a really important question, and it comes up quite a bit. The motivation or the reasoning behind using a lower threshold for level of service for roundabouts as opposed to signals is that there's no guarantee for service. So sitting at a red light at an intersection, you know that eventually the light will turn green, and while it's red, you can move on to other things and you can relax a little bit. Versus at a roundabout where the queue continually moves up, it's a more active waiting, and the reasoning or the thinking here is that therefore the delay experienced at a roundabout is more severe than that at a signal. And so that is maintained also for the interchange application. So this is consistency with the rest of the chapter. It is brought up quite a bit as a potential point of criticism, where presumably roundabouts are being held to higher standards than signalized intersections. There was not sufficient data and evidence and research to suggest a change. There was no clear quality of service study that has ever been done to suggest otherwise. The thing I would really like to emphasize is to really bring it back to the broader ICE framework, where even if the roundabout level of service in the peak 15 minutes may be a little bit worse than that of a traffic signal, the ICE framework really allows the roundabout and some of these other intersections to shine, because they will end up performing so much better on the safety perspective, so much better on the life cycle cost perspective, that hopefully some of these slight differences in the level of service thresholds are going to be well made up by the fact that some of these intersections have such tremendous safety performance.
Great, thank you. The next question is RQ 50% or 95%?
The Q length equation in the HCM is based on the 95th percentile Q. So RQ, well, that equation could be modified to calculate a different percentile. The default is the 95th percentile.
Great, thank you. Should modified LOS thresholds be considered for all intersections working in clusters, or only for interchange clusters? How about for CFI, continuous flow intersections? Should modified LOS thresholds be considered for all intersections working in clusters, or only, I'm sorry, am I repeating? Yep, it was copied twice.
Yeah, the question was shown twice, yeah. So the level of service framework with the ETT, experience travel time, really applies to all clustered intersections. So even for the CFI, as a movement goes through multiple signals, they would all be added together. So the way these are added is a little bit different as a CFI than for an ARCUT, but the method stays the same. And really the committee wanted to make sure that the framework is not only limited to the types of interchanges and intersections that are currently part of the chapter. For example, we don't have an explicit method for quadrant roadways, but quadrants are, at least being talked about. We have 2 or 3, maybe 4 open to traffic across the country. And so as quadrant roadways, J-turns, jug handles become more popular, the same framework can be applied to those as well. And so there's some discussion offered in the manual to emphasize that.
Great, thank you. All right, so the next question. I have a question with regard to LOS thresholds for the new intersection interchange methods. What research was used to assign LOS values to certain delay numbers? The 1.5 times rule for DDI seems arbitrary.
Let me jump in here, Bastian, on that one.
Mm-hmm.
It is arbitrary. With the thinking is that, and we on the committee had a lot of discussion about it in developing the method, and the thinking was at an interchange, some drivers will pass through both intersections, some through only one, and so it was arbitrary. Well, let's just take the scale for a signalized intersection and multiply it by 1.5. Typically, with a research project, one of the things that we do at the end is identify, what else could stand some additional research, and that might be one area where those, where that could stand a little bit more research, and particularly those thresholds other than when we have V over C equal to 1, which we have set as the threshold for level service F. But yeah, it's a good question, and sometimes just based on where we are in development of the method and the resources available, sometimes you get to arbitrary decisions like that, and that's what went behind that decision.
Great, thank you. How does the HCM provide a method to calculate a total intersection VC ratio for alternative intersections?
The V over C ratio is calculated for each movement or for each origin-destination pair through the intersection or interchange. So the V over C is not aggregated to the intersection level. The CapEx tool, the planning level tool, does that aggregation to give a general V over C, and I guess it's based on a volume-weighted average. For the HCM, since the V over C is used to flag any OD pair that's over capacity, there's no need for that aggregation. The actual control delay is aggregated for the interchange and intersection to get an overall level of service, and that aggregation is done based on volume weighting. So each individual delay multiplied by the respective volume.
Great, thank you. Okay, so the next question is, I went to the Volume 4 website. I downloaded the spreadsheets, but could not figure out which document had the instructions for the spreadsheets.
Yeah, Volume 4, those spreadsheets I think you're talking about are the computational engines that were used as part of the research. The committee decided to make that information available to users, but one of the things that separates a computational engine from commercial software is documentation, and so we didn't include any documentation. It's probably one of those things that as we get more comments on that, we may go back and try to add that. But I would say that if you have a question about that, submit that through the website, and we'll see if we can address that. And then Bastian, feel free to add anything to that.
Yeah, I think that's correct. There are two computational engines that have more documentation. The one for freeway facilities and one for urban street facilities. But some of the other spreadsheets that were used as part of the research to develop and test the methods, they have been made available as resources. But as Tom mentioned, they are without without support, and that's partly also because the HCM does not really want to compete with commercial software. The spreadsheets were there to also help commercial vendors test their own implementation of the method. So that's why they're available to make sure that if somebody wants to, develop software that implements these, that they can test them against the spreadsheets. And we worked fairly closely with some of these software developers to do that. But yeah, they're not commercial grade software, and other than reaching out to the subcommittee, which is probably a good plug here to use the website and to become a member or a friend of the Highway Capacity Committee and the various subcommittees. That's really a great way to also get some more information about these methods and exchange information and all that. There's also a discussion board on hcmvolume4.org, which can be used to pose questions like this.
Great, thank you. The next question, please provide more information on the mobility topic of new, more bike and pedestrian opportunities. That is with regard to the benefits of ICE via innovative intersections. Is it just the reduction of conflict points, or are there other tangible opportunities as it relates to bike and ped?
Yeah, so the highway capacity manual methods in general include a large portion of multimodal performance assessment methods. So there are, it's not unfortunately there for all chapters, but there are methods to evaluate, for example, the delay of pedestrians at a signalized intersection. There are methods to evaluate the quality of service of pedestrians or bicycles traveling along an urban street. Some of these methods have not been specifically customized for the alternative intersections. However, they still provide at least some empirical basis for quantifying delay, quantifying travel time of pedestrians traversing through these various intersection forms. Roundabouts is another example. I think for the broader ICE implementation and the multimodal impact, there are other ways and maybe better ways to also look at the multimodal accommodations. Unfortunately, there aren't a lot of safety models available to date, but yeah, looking at conflict points, looking at severity of conflicts, whether those conflicts are for free-flowing movements or for yield-controlled movements, for example. I think this is where the Federal Highway Alternative Intersection Interchange Guides can really be useful as well, because each of those guides has a multimodal chapter early on that really provides a lot of good information. So the HCM can provide some added detail, but if you're truly interested in some of the ped bike safety implication, it probably falls short of everything you would need for a full ICE framework. And I know several states are working on overcoming exactly that question.
And Bastian, this is Jeff. Could I also weigh in on that question? I think also to talk about the opportunities that the ICE approach offers a designer or a planner, and what we've learned so far with these innovative designs is that they can create opportunities to integrate pedestrian and bicycle facilities in ways that, quite frankly, make it easier to include them. And so I think perhaps the best illustration of that has been the very positive experience we've had with the majority of diverging diamond interchanges. When you talk about service interchanges in urban and suburban environments, they're notorious for being not pleasant places to walk or bike. And yet with the DDI, not only can an agency fix what is probably a congestion and safety problem, they can also carve out the space to provide a very pleasant walking area and also on-street bicycle lanes or shared use paths, whatever the case may be. And we've also learned that because these designs, because of their synchronized movements, whether they're because of signals or the slowed movement of traffic due to the geometrics, those translate to benefits for pedestrians and bicyclists as well. So, I think it's, as Bastian said, are the models as far along as we would like? No, and part of that challenge is that data is terribly difficult to acquire. But that said, there are still many, many best practices for peds and bikes that are easier to apply at these innovative designs. And so, you know, it can often be a win-win.
Great, thank you. So we have maybe like 4 or 5 more questions that have come in, maybe 6. So just to let you know, we'll answer one more question. We'll go over how to earn PDH credit one more time, as I did before the webinar, or after the webinar began. And then we will try to answer as many questions as possible within 5 minutes after the webinar ends. The end time of today's webinar, 10 minutes at the most. All right, so one last question before I go over how to earn PDH credit. How is EDTT accounted for or reflected in the LOS results for alternative intersections?
Yeah, so the EDTT, or extra distance travel time, is added to the control delay. So if let's say a movement experiences 30 seconds of control delay and 10 seconds out of direction travel time, then 30 plus 10 gives 40 seconds experience travel time, or ETT, and that's the one that's used in the level of service lookup table.
Great, thank you. So very quickly, in case you joined a few minutes late, to verify your attendance, please write down these event attendance codes. If your last remaining questions, and then we will call it a day. Hold on one moment, let me pull them back up. Okay. While not specifically an intersection situation, is a methodology being developed to analyze two-way center turn lane conditions?
There's an ongoing research project that looks at operations of two-lane highways, including with passing lanes, which is a little bit different than the application here. So no, there's no, that I know of, there's no specific method in development to look at two-way center turn lanes. I think they would be, treated as two de facto left turn pockets. So you would take the two-way center left turn lane and divide it into, approximate turn pocket lengths, and then evaluate them that way.
Great, thank you. Why? Oops, hold on one moment. I just realized my screen was paused. I apologize. If you would like to see what I was referring to when I discussed how to earn credit, my screen is no longer paused. I apologize for that. The next question on is, why assign LOS if there is no research to support it? Unresearched and old LOS thresholds now being applied willy-nilly to these new methods, and roundabouts for that matter, really call into question the relevance of this aspect of the HCM.
That's a good question, and it's one that's been discussed. The whole level of service issue has been discussed among the committee for a long time. We have attempted to do that through past research, and it can produce some results that are all over the place. For one thing, you can show one scenario to a whole room full of people and get a whole distribution of LOS, for example. And you get other things like, truly things like street trees that people, associate with quality of service. So it's not a simple issue. The one thing that the committee has done with all the methods now is whenever we get a VC ratio of 1.0 and greater than that, we've said that that's LOSF because the expectations are matched up with this. But past efforts to do research on human factors research and to correlate that with quality of service that is stratified through the LOS scale has been very difficult, actually, and so historically it's been subjective, but using the best judgment of the researchers and the committee, it seems like it's a simple issue, but determining actually what that is pretty complex, actually.
Great, thank you. Can you clarify, a SPUI would have ETT LOS thresholds of 1.5 times signalized intersections, but a full MUT intersection would simply be 1 times signalized intersection thresholds, correct? Seems illogical.
Yeah. The assessment is correct. So any of the interchanges have thresholds that are about 1.5 of a signalized intersection versus all the at-grade alternative intersections are the same as a conventional signalized intersection. The motivation behind that is that presumably interchanges would be compared to interchanges, intersections would be compared to intersections. Now, I recognize fully that that's not always the case. In fact, we have quite a few projects in the town I live in where there's evaluations being done right now that directly compare an interchange to an intersection, and then presumably they have different level of service thresholds, which emphasizes the need and the difficulty of that level of service metric. The committee discussed, as Tom mentioned, various ways to solve this. And unfortunately, alternatives such as, for example, changing the level of service for all signalized intersections for something else would have had very far-reaching implications for the practice in this country. And so they really were not deemed to be feasible. And then we have a lot of state and MPO municipal representatives on our committee. So ultimately we came up with really this compromise in a way, and I really would like to again emphasize that level of service I know is a very convenient number, and I know the HCM has a lot of legacy of providing it, but really the HCM as well as other analysis tools provide a whole host of performance measures. And so I would encourage, as states are looking at ICE policies, to really look beyond just that one letter grade, which even though it's convenient and may be needed for efforts like a statewide prioritization where you compare hundreds and thousands of projects, for a project level assessment and determination, really there are other metrics that much better express and quantify the operations of an intersection versus another one. And while I know level of service is tied to policy in a lot of locations, really ICE is one way to overcome some of those, frankly, sometimes outdated ways of looking at things, to really not only look at the peak 15-minute level of service, which is really what we're talking about when we say HCM, but moving beyond that to look at whole day performance, life cycle cost, safety impacts, user impacts, quality of service measures, where really the operational performance as predicted in the HCM becomes one of many performance metrics that are part of an ICE evaluation.
And I'll just quickly add to that we now at least have the platform for evaluating an urban street as a system the way that it truly operates. We've been able to do that using simulation before, but the simulation is not based on the empirical research, as Bastian mentioned earlier, that the HCM methods are. And so there's been an evolution of process from signalized intersections to an urban street, which is a collection of signalized intersections, and now being able to fold in an interchange with a freeway, whether it's a conventional diamond or DDI or alternative intersections. So the practice is evolving. We're not there yet. We don't have to do everything. In fact, we have a more robust tool set with deterministic methods than we've ever had before, those methods being based on research, but we still have a ways to go.
Great, thank you so much. And the last question, please repeat the name of the document mentioned to add multimodal analysis to alternative design analysis.
Well, so I think the question is talking about the Federal Highway Alternative Intersection and Interchange Guides, which were included as part of my presentation that you can download in the docket on slide 12, and there's a link. Those volumes provide more qualitative than quantitative information. So there's really helpful resources in there and discussion that you can use to inform your decision. There's no quantitative information for multimodal analysis in there. There's actually another national research project, NCHRP project 7-25, pedestrian and bicycle accommodations at alternative intersections, that is about to get started here in the next few weeks. And that project will, over the next 2 years, really look at pedestrian bicycle accommodations and presumably also have some sort of an evaluation system or a tool or a scoring matrix that comes out of it in the end to assist this project. But unfortunately, that research is just now getting underway.
Great. Thank you. So that concludes today's ITE Learning Hub webinar. Thank you so much for joining us today. There was a really great high-level of participation from all of you. Some great questions coming in. Thank you to the presenters for helping field all of the questions that came in today. We had some really great presentations as well. So thank you again, and we look forward to seeing you all at our next webinar, webinar 8.